In the last video, you were introduced to the chair conformation of cyclohexane. In this video, we'll look at the ring flip, or the interconversion of the two chair conformations of a cyclohexane ring. And those two conformations are shown here at the top of this slide. Before we go any further, I'll encourage you to find or to build your own model of cyclohexane with two different colored hydrogens. One color for the axial positions and one for the equatorial positions. And I'll show you this ring flip or interconversion between conformations first with my model. And I'll use the model where I have all of the axial hydrogens with pink bonds and all of the equatorial hydrogens with green bonds. And here I can do what's called a ring flip. And in a ring flip, the top pointing or up pointing carbon bends down, and the bottom or down pointing carbon bends up. Okay. And when this happens, the hydrogens that were equatorial become axial, and those that were axial become equatorial. And you can see that those axial hydrogens that were pink are now equatorial, and the equatorial hydrogens were green, and those have become axial. Okay, I'll do it one more time. I'll take the up pointing carbon and flip it down, and I'll take the down pointing carbon and flip it up. Okay, and again, that interconverts the axial and equatorial positions. We'll draw that out here. And we'll take a minute to relate these two different conformations of cyclohexane on paper or on the screen. Okay, and first we'll relate the carbons. Remember we said that the up carbon, here that's carbon 4, bends down, and the down carbon, here that's carbon 1, bends up. Then we can place our hydrogens. And I'll start with the axial hydrogens in red, and I'll place the equatorial hydrogens in blue. And now when the ring flips from the left conformation to the right conformation, the axial hydrogens that were pink become equatorial, and the equatorial hydrogens that were blue become axial. But the up hydrogens stay up and the down hydrogens stay down, and that's super important. So we can see here that on carbon 3, for example, the blue hydrogen was up, it was equatorial and up, and then when the ring flipped, on carbon 3, the blue hydrogen is still up, but now it's axial and up. And you can check that for each hydrogen in the structure. The up hydrogens stay up and the down hydrogens stay down. And for cyclohexane without any substituents on it, the two chair conformations have the same energy, the same stability. But when we put substituents on the ring, the two chair conformations may no longer be equal in energy. And we'll see that here using methyl cyclohexane. In the wedge dash drawing, I placed the methyl group up. So when I draw my chair conformation, I'll still place the methyl group up. In this chair conformation, that puts the methyl group in the axial position. Now if we do a ring flip and draw the other conformation of methyl cyclohexane, the methyl group will be in the equatorial position. Okay, and in this first conformation, with the methyl group in the axial position, we have what we call 1,3 diaxial strain, or sometimes called A13 strain. And this is the steric strain that we noted at the beginning of this lecture series. And it arises from groups that are 3 bonds apart, but very close in space. In the other conformation, the conformation on the right, that places the methyl group in the equatorial position, the diaxial strain is relieved, and so the second conformation is more stable or lower in energy, because it eliminates that strain, that steric strain. Finally, let's look at 1,2-dimethylcyclohexane. Now in this case, we have both cis and trans stereoisomers, so we'll need to draw both. I'll first draw them using the wedged dashed depiction. Remember that cis places both groups on the same side of the ring, so I'll place them both up here. And trans places them on different sides of the ring, so we'll put one above and one below the ring. Then we'll convert each structure to its corresponding chair conformation. In the case of the cis disubstituted cyclohexane, we have one group up, and I'll place it in the axial position. And then the next group is also up, which means it will be in the equatorial position. So here we have one group axial and one group equatorial. Now for the trans disubstituted cyclohexane, I have one group up and one group down. I draw them on the chair conformation, and it means that I have two axial groups. Okay, now let's do a ring flip to draw the other conformation of each ring. We'll start with the cis disubstituted cyclohexane. And after I do the ring flip, I find that I still have one group axial and one group equatorial. So for the cis disubstituted cyclohexane here, both conformations have the same energy because they both have one axial and one equatorial methyl group. In the trans disubstituted case, however, the second conformation has both methyl groups in the equatorial position. This is the conformation with the least diaxial strain because we don't have a methyl group in an axial position. And so this conformation will be the lowest in energy between the two. Let's end this lecture series with the question we posed at the beginning. To draw both chair conformations of cis 1-tert-butyl 4-chlorocyclohexane, and then determine which conformation is most stable. First, I need to draw a dashed wedged drawing of the structure. Then I can convert that into a chair conformation. In my drawing, I placed both of the substituents in the up position. So in my chair, they both need to be pointing up. And I always find it easiest to place a substituent on the carbon that is far to the right, because I know that this carbon has an axial up group and an equatorial down group. So to place the tert-butyl up on this carbon, it's axial. And then to place the chlorine on the opposite side of my ring, 3 positions away, it's also pointing up, and so here it must be equatorial. In the second conformation that I get after I do the ring flip, the tert-butyl group that was axial will now be equatorial, and the chlorine that was equatorial will now be axial. So now to compare the energies of the conformations, I'll remember that the more stable or lower energy structure will have the least diaxial strain. So it will place the most groups and the largest groups in the equatorial positions. Here the tert-butyl group is much bigger than the chlorine. So the conformation that places the tert-butyl group in the equatorial position will be the lowest in energy or the most stable conformation.